Welcome to this video about center of mass and collisions. Understanding the center of mass can greatly simplify how we analyze and solve collision problems in physics. First, let's define what the center of mass is. The center of mass, or CM, is the point that represents the average position of all the mass in a system. Mathematically, we can find the center of mass position vector by taking the weighted average of all individual mass positions. Let's visualize this with a simple example of two objects. Here we have two masses, m1 and m2, positioned on an x-axis. If I tell you that m1 is 2 kilograms and located at x equals -1 meter, while m2 is 1 kilogram at x equals 2 meters, we can calculate the center of mass position. The center of mass would be located at x equals 0 meters, which makes sense as the heavier mass pulls the center of mass closer to itself. Now, let's discuss why the center of mass is so useful when analyzing collisions. The key insight is that in a closed system with no external forces, the velocity of the center of mass remains constant, regardless of what happens inside the system. This is directly related to conservation of momentum, which states that in the absence of external forces, the total momentum of a system remains constant. Let's visualize a collision to see how the center of mass behaves. Here we have two masses about to collide. The blue mass is heavier, moving slowly to the right, while the red mass is lighter and moving quickly to the left. Let's mark the center of mass of the system with a yellow dot. Now watch what happens during the collision. Notice how the individual masses change their velocities, but the center of mass continues moving at a constant velocity. After the collision, the masses are moving differently, but the center of mass continues along its original path at the same speed. One of the most powerful techniques when analyzing collisions is to transform the problem to the center of mass reference frame. In the center of mass frame, the total momentum is always 0. This often simplifies the calculations. To transform to the CM frame, we simply subtract the CM velocity from all object velocities. Let's reconsider our previous example. In the CM frame, the blue mass would be moving to the right with a velocity of v1 minus vcm, and the red mass would be moving to the left with a velocity of vcm minus v2. The CM frame is particularly useful for elastic collisions. In an elastic collision, both momentum and kinetic energy are conserved. In the CM frame, an elastic collision simply reverses the velocities of all objects. After solving the problem in the CM frame, we can transform back to the original frame by adding the CM velocity back to all object velocities. The center of mass concept is especially useful for systems with multiple particles. For example, in an explosion where an object breaks into many fragments, the center of mass of all fragments will continue to move as it did before the explosion, assuming no external forces. Speaking of external forces, if there are external forces acting on the system, the momentum is not conserved, and the CM velocity will change according to Newton's second law. The net external force equals the total mass times the acceleration of the center of mass. Let me summarize the key ideas and problem-solving tips for using center of mass in collision problems. First, if there are no external forces, the velocity of the center of mass is constant. Second, internal forces don't matter for the motion of the center of mass. They can change individual object velocities, but not the CM velocity. Third, transforming to the CM frame often simplifies collision problems because the total momentum is 0 in that frame. Finally, remember to apply conservation laws alongside the center of mass concept. For all collisions, momentum is conserved if no external forces. For elastic collisions, kinetic energy is also conserved. And that concludes our discussion of center of mass in collision problems. Understanding how to use the center of mass concept can greatly simplify your analysis of complex collision scenarios. Remember that the CM gives us a way to treat a system of multiple objects as if it were a single point particle, making many problems much easier to solve.